The definition of reflection. It is the bouncing of a wavefront back into the original medium, or the change in the direction of a wavefront at the interference between two different media. You can see from the image that a traveling wave or a pulse encounters a rigid boundary and is reflected in such a situation. When a wave strikes a boundary between two materials, the change in the direction of its propagation is called the reflection of the wave. There are two types of reflection, which is a free end and a fixed end. A pulse with an upward displacement will reflect off the end and return with an upward displacement in free end reflection. If you could see in image A, the right end of the string is attached to a ring that slides up and down on a road without causing any friction. Hence, the name is free end. And if you could see in the picture B, it is a fixed end, which is a situation in which a piece of string is attached to a rigid wall at its right end. The law of reflection. As you can see from the equation, the angle of incidence is equal to the angle of reflection, and the second one is incident ray, reflected ray, and the normal drawn at the point of incident to the reflecting surface lie in the same plane. The example of reflection. The first one, we have the reflection of a wave sound, which the example is echo. And the second one is the reflection of light, which is a light reflecting a mirror.
Definition. In physics, refraction can be defined as the change in the direction of a wave passing from one medium to another. Some of the most common phenomena of refraction include the refraction of light, sound, and water. Refraction is the main principle that is used for making optical instruments such as lenses and magnifying glasses. Additionally, refraction allows human eyes to focus light onto the retina. Law of refraction. First, the incident ray, refracted ray, and the normal all lie on the same plane. Second, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant. This is also known as Snell's law of refraction and can be written as sin I over sin r equals a constant. Causes of refraction. Due to the different density, a wave has a different velocity when it enters a new medium. The ratio between how fast light travels in a medium and a vacuum can be represented by a refractive index, denoted by n and is given by n equals to c, or speed in vacuum, over v, or speed in medium. Based on the refractive index of the medium, it can be concluded that the change in speed results in the change of direction, or simply known as refraction. Examples of refraction. Since the light refraction causes the light coming from the pool's bottom to bend at the surface, a swimming pool always appears shallower than it actually is. Second, refraction can be seen in the rainbow that results from the sun's rays bending to raindrops. Third, due to light refraction, when white light enters a prism, it is separated into the colors red, orange, yellow, green, blue, and violet.
Diffraction is a condition when wave pass through a gap that becomes the barrier. When wave pass through it, this can cause the wave to experience deflection, flexing, and spreading that cause the changing of direction of the wave. The number of waves that will experience deflection depends on the size of the gap. When the gap has a narrow size, it will make the wave spread wider. This can make diffraction easier to be seen and to be observed. However, when the gap has a wide size, this can make diffraction to look more unclear due to the number of waves that will experience deflection are getting smaller. Diffraction has 5 types which are classified based on how it produces the diffraction wave. In here, we need a wave source, a gap, and a screen to observe the diffraction pattern as the result. These are 5 types of diffraction. First, there is Fresnel diffraction, which is a diffraction in which the wave source, slit, and a screen are placed close to each other. It uses a slit with wide length and sharp edge. Due to close distance, the resulting wave will be curved and the intensity of the diffraction pattern will keep changing as the wave moves from middle to the edge. Second, there is Fraunhofer diffraction. It is different from Fresnel diffraction since this diffraction places the wave source, slit, and a screen far from each other. The diffraction pattern will always have a constant intensity and resulting flat wave. Next, there are single, double, and multiple slit diffraction. These 3 diffractions are actually the same, but the things that differentiate them are the number of the slits. Here, single slit will produce dark pattern, while double slit produce dark and light pattern, and multiple slits will produce bright pattern. But three of them will produce new waves that will interfere with each other to make the diffraction pattern. Law of diffraction is called as Bragg's law, which was introduced by William Lawrence Bragg in 1913. It happens when X-ray touches the surface, it will form electromagnetic radiation wave. Then it will radiate another new wave with the same angle. This will only happen when the wavelength is proportional with the distance of the atom in the surface. The application of Bragg's law can be seen in XRF and WDS. Here I also include the equation of Bragg's law. Examples of diffraction can be classified into water, sound, and light diffraction. Water diffraction can be seen when we use faucet water in the toilet, while for sound diffraction, it happens when a person calls from far and it is getting blocked by an object, but still can be heard by us due to diffraction. Next, for light diffraction, it can be seen when a light entering a dark room.
Okay, interference. Starting from the definition, when two waves traveling through the same medium collide at the same point, the phenomenon known as interference occurs. As a result, a brand new pattern will emerge. Then the amplitude of the subsequent waves may be greater or less than the first two waves, and these first two waves we call it as parent wave. In spite of the fact that interference occurs when waves collide with one another and create a net shape in the medium, the waves will continue traveling in the same direction they did prior to the interference, like the figure here, the below one. And in this way, each wave maintains its characteristic before and after the interference. The medium's displacement at any given point when two waves collide is equal to the algebraic sum of their individual displacement at that point. So let's take an example from the figure here. Suppose plus A has plus 1 unit of displacement, right? And the same goes for plus B, of course. So the amplitude of the resultant wave will be plus 2 units. Okay, constructive interference is one of the two types of interference. Constructive interference happens when two waves overlap in such a way that they combine to create a larger wave, so the greater the amplitude. And constructive interference can be observed when two interfering waves are displaced upward, like in the left. However, when both of the interfering waves are pushed downwards, it's also visible. Okay, destructive interference is the other type of interference. If the pulses are on the opposite sides of the equilibrium position and meeting each other in the same position, this condition can lead to a phenomenon called disruptive interference, and it divided into two types. The first one, complete disruptive interference, is when two pulses have the same displacement but in the opposite direction and meeting each other, so they will cancelling each other out and the resultant wave has zero amplitude. But keep in mind that this cancellation doesn't make the wave stop. After the cancellation, the parent wave will start going towards their original path. Because wave isn't matter, so it will not break or anything if it's collide. And the second type, incomplete disruptive interference, is when two waves having different maximum displacement and on opposite direction, so the resultant wave's amplitude will not be zero. It's just less than the parent wave. Okay, last one. Let's give an example of how noise cancelling headphones work. The first one, the microphones detects the background noises, and it processes the signal accordingly, and then reproduce the noise just out of phase with the signal. As a result, the resulting noise is zero, or at least the sound waves reaching your ears are greatly reduced.
Polarization in waves are light waves in which the vibration occurs in a single plane. Longitudinal waves can be polarized, and only transverse waves that can be polarized. Longitudinal waves are when the direction of the oscillation is parallel to the direction of the wave, while transverse waves are when the direction of the oscillation is perpendicular to the direction of the wave. There are three main types of polarization: linear polarization, circular polarization, and elliptical polarization. Linear polarization is when the oscillation of a wave is constrained to a single plane. Linear polarization can only be done by using a polarizer, which only allows waves that are parallel to the polarizer to pass through. Linear polarization consists of two types of polarization, which are vertical and horizontal. Circular polarization is when two linear components in the electric field of light are perpendicular to each other, and their amplitudes are the same, where one of the waves is outphased by a 90-degree angle, and the other wave has an amplitude of 0 degree. And there are two types of circular polarization, which are right-hand circular and left-hand circular. elliptical polarization is the same as circular polarization, where two linear components in the electric field of light are perpendicular to each other, except that the amplitudes and phase differences are not the same. One of the waves is out of phase by an angle that is not 90-degree angle, which means that the other wave also has an amplitude that is not zero. There are two types of elliptical polarization, which are right-hand elliptical and left-hand elliptical. Malus' law is named after Louise Malus, who discovered it. In polarization of waves, Malus' law helps us to study the relation between light intensity and polarizer and analyzer. There are some important points that we should remember about Malus' law. The first one is when unpolarized light is incident on an ideal polarizer, the intensity of the transmitted light will be exactly half of the incident unpolarized light, no matter how the axis on the polarizing is aligned. The second, an ideal polarizing filter passes 100% of incident unpolarized light, which is polarized in the direction of the polarizer polarizing axis. There are three formulas of Malus' law. The first one is intensity is directly proportional to the amplitude squared. The second one is intensity 1 is the same amount as the half of the original intensity. And the third one is intensity 2 is the same amount as the intensity 1 times cos squared theta. There are a few examples of polarization wave in daily life. The first one is sunglasses. Polarization is used in sunglasses to reduce the glare. The second one is in three-dimensional movies or 3D movies. Three-dimensional movies are produced and shown with the help of light polarization. And the last one is polarization are in infrared spectroscopy and in seismology to study earthquakes.
Definition of electromagnetic waves. Electromagnetic waves are waves that are created as a result of oscillations between an electric field and a magnetic field. An electromagnetic wave has a perpendicular electric and magnetic field. Unlike mechanical waves that require medium to travel, the medium's particles are not necessary for the propagation of electromagnetic waves. The electromagnetic field is created by an accelerated charge. This electric field acts as a force on the other charged particles. Positive charges accelerate in the field's direction, while negative charges accelerate in the opposite way. These accelerated charges are what generate the electromagnetic field. Characteristics of electromagnetic waves. First, since they propagate by changing the electric and magnetic fields to make them perpendicular to one another, electromagnetic waves are transverse waves. Second, the creation of electromagnetic waves involves accelerated charge. Third, the propagation of electromagnetic waves does not require a material medium. Fourth, the frequency of electromagnetic waves is unique. Their frequencies remain the same, but their wavelength change as they travel across different mediums. Fifth, electromagnetic waves follow the superposition principle. Examples of electromagnetic waves. Electromagnetic waves are divided by their frequencies. In our daily lives, many waveforms serve as a variety of purposes. Visible light, which enables us to see, is the most significant of these. Some of the examples include, first, radio waves. The lowest frequency waves in the electromagnetic spectrum are radio waves. The signals received by television, radio, or cell phone are transmitted by radio waves that are produced by radio stations, television stations, and mobile phone businesses. Second, microwaves. The second lowest frequency waves in the electromagnetic spectrum are microwaves. Microwaves are beneficial for communication because their higher frequency allows them to pass through smoke, clouds, and light precipitation. Microwaves are used in radar that aids in weather forecasting, food preparation, and information transmission. Third, infrared. Infrared waves lie between microwaves and visible light. It is possible to divide infrared radiation into near and far categories. The waves with wavelengths closest to visible light are known as near-infrared waves. The wavelength of far infrared radiation is further distant from that of visible light. Far infrared wavelengths produce heat because they are thermal. Infrared light is produced by anything that produces heat, including the human body. Fourth, visible light. The range of wavelengths is visible that the human eyes can see is covered by the spectrum. Visible light has a wavelength that varies from 390 to 700 nanometer. Humans see the colors of the rainbow as different frequencies of visible light. Frequencies span from low visible wavelengths that are regarded as being red to high visible wavelengths that are perceived as being purple in color. Fifth, ultraviolet. The ultraviolet radiation from the sun can lead to sunburn and even cancer in living things. A process involving high temperatures emits UV radiation. Bumblebees are one insect species that can see UV light. 6. X-rays. Sources that generate extremely high temperatures, like the sun's outermost part, emit X-rays. Exceptionally energetic cosmic occurrences, including supernovae and black holes, are natural producers of X-rays. They are used in medicine to capture X-rays of bones, because they can penetrate soft tissues like skin and muscles. 7th, gamma rays. An electromagnetic wave's energy increases as its wavelength decreases. The shortest waves in the spectrum, gamma rays, have the highest energy. Gamma rays are occasionally used to treat cancer and to capture precise images for medical diagnosis.